So the idea today is to not explain any of the theory behind how the stuff is working, just what you can do with trace points and how you might choose to do them. And we're going to focus primarily on having no tools, meaning I've got ls, I've got cat, I've got less. I haven't got high-value tools, and what that means is that everything I'm showing in the beginning part of the presentation will work in busybox, toybox, the smallest build route you can summon, or on an Android system. I'm going to start off by showing just a reminder for people, if they are not familiar with it, of the ftrace system itself. We're not going to talk about ftrace much, but just to give you an example of what's happening in the tracing directory. So we have a tracing directory here. I'll draw your attention to the README. So there's about 3 key things you should remember when you go home. One of them is that inside the tracing directory in debugfs is a file called README, which tells you how to use ftrace. So even on your Android system on its own, you've even got enough of a manual to remember how to do the tracing without going to anywhere else. And just as an example, for people who haven't seen it before, we can sort of go to function, put it into current tracer, and that will set the function trace running. And if I look in the trace file, I can see tremendous output. A lot of it is making my screen update in front of me. That's the sort of quick idea that you can see I'm just echoing to and from files to turn things on and off. And that's actually all we're going to do for ftrace. I was in a presentation with Stephen Rosett late last year where he called ftrace boring because we've all seen it before. And so while it is awesome, if you haven't seen it before, then please find a way to play with it. We can also turn tracing on and off by, oops, sorry, that's been echoing 0 to it. And the other thing I was pointing out that I was reading from a file called trace before, and reading from trace is non-destructive in the sense that if I keep reading from it, I can keep seeing the same data over and over again. There's also trace pipe, which will consume the data as we look at it. And through the rest of the presentation, I will be working with trace pipe, and once it's finished updating my screen, that will stop moving. Oh, it's not, because I haven't turned the tracer off yet. And the final thing I'm going to say as part of the kind of setup is that I am going to put myself in a little macro, because whenever you're doing a live demo with ftrace, you will turn something on and then forget that you've turned it on, and then everything will go very swiftly off the rails. So I'm just going to the debug directory in my macro to make sure even if I'm in the wrong directory, it will still work. I'm going to turn the tracer off while I do some work on it. And I'm going to then reset everything to kind of factory defaults, which means setting the current tracer to no op. I can turn off any events that are enabled. So I will turn on events as we go through the tracing system. That will turn them all off again in one big hit. If I've got anything dynamic set up, I'm going to clear out anything dynamic. Of course, if I make a spelling error here, it will look rather bad. And then I'm going to turn tracing back on because tracing is on by default. And then finally, I'm going to clear out the trace buffer so it's not in the way. And when I type trace reset at any point then, roughly speaking, with a few corners that I've cut to make that quicker for me to type, that's going to take me back to a factory kind of default positions. So, fantastic trace points and where to find them. The second take home, and if I was running late, the entire rest of the presentation, if necessary, is find events type D. That is the set of fantastic static trace points in the kernel and exactly where to find them. We're just looking in the events directory and looking for directories. On this particular machine, I think I've got about in the order of sort of 1,600 trace points. My Intel laptop over there has closer to 2,000. But that's because I'm running a slightly cut down kernel on this machine to make it easier for me to build it frequently. So you could all go home at this point, but I have got a few more things to show if you're interested. So I've had to try and pick examples that you will find intuitive. So when I say these are fantastic trace points, they are, but they have been selected because they're ones that you ought to find fairly intuitive about what's happening on my machine as we look at them. So I haven't gone deep into the bowels of the scheduler and other things that you can look at if you're a power engineer or interested in what's going on. I've picked things that should be intuitive. So the first one I'm looking at is Reg Map. So Reg Map is a register abstraction API, and every time you access a register through the Reg Map in directions, you get log messages. So on this particular laptop, the reason I've picked it is because it has some interesting things happening in the Reg Map. It's more common in the ARM world to be using Reg Map because the drivers are ultimately a bit newer. So in this particular thing, I have these devices which are hooked up to Reg Map. And I believe they're particularly using Reg Map because it allows you to get to the PMIC with a nice clean interface. And there are files all over the events directory to turn things on in mass. So if I go to the Reg Map folder, enable in there, then every Reg Map trace point will just have been turned on in one shot. And when I look at trace pipe, I'll start to see lots of readings coming in as my thermal sensors are read, my battery levels read, and other things. However, it's getting a bit busy. I can't read it terribly well. So to try and reduce the volume just a little bit, I'm going to do a kind of globbed match so that I only get thermal sensors, I don't get any other noise. And I can write that into the Reg Maps filter, and then similarly, all the register maps, if they have a name property, will be using it to filter out some of my details. I can look at my trace pipe, and now I can only see thermal information. Possibly I'm only looking at a single thing, so I can tidy up some more. I can put the address of the particular, it's actually, it's a name, but since the name is derived from the address, that's the same thing. And I can even track down by register as well. I could say I'm only caring about the OXC register. And again, I can now look at my trace pipe, and now I'm getting just the single register access happening each time. I can see the value coming back. So I can use that to digest the filter and prevent myself drowning information. Of course, you can use grep to do these things as well. But that's one of the techniques is we can use to filter things. So that's all we're going to do on Reg Map, but that was a nice, quick, easy introduction. We're going to amp things up very slightly by looking at I2C now. Anybody doesn't know that a modern laptop, the keyboard, the mouse, the touchscreen will all be hooked up by I2C. So you get loads of lovely I2C activity on machines like this, which again makes it easy for you to intuit what I'm doing. So I can go in and I can turn on the I2C logging, I2C place points. Again, I'm doing it en masse. I could go into each individual directory and turn on only the ones I'm interested in. But if you're starting with the trace points, you tend to put the whole set on, look what you see in the logs, and then start refining things based on what you're kind of getting used to, what you need to know. So what we see on this one, what we see on this one is that for some reason something is hammering away all the time on this particular I2C device. What I learned on my Intel laptop is that it has a capacitive sensor I never knew it had, because every time I touch my hands on the deck, there was I2C messages, and I took them away and they go away again. And I didn't even know it had that feature, and I still don't know how to exploit it for anything useful. I suspect it's for thumb rejection, but it doesn't reject the thumb very well. But I can type the keyboard and we see an increase in activity. So we know that whatever it is it's polling I2C really hard. I think that's because there's actually fingerprint sensors and other things attached to the keyboard on this device. I can waggle my trackpad, I can touch my touchscreen if I keep away from the screen. You can see these things come and go, and I can trace on them. And just as before, if I want to look at a particular adapter number, now in this case, I2C11, I'm not quite sure how to filter on that. So if I want to make my life a little bit easier, I can look at events, I2C, and I'm going to look at the I2C reply, which is where we get the data from the, we've just read from the keyboard, that's where the thing actually puts out the hex dump of the packet we've just received. And I'm going to find out what the format of the trace point is. So this allows me to, this allows me to look at the format of the trace point. And I can see that I've got some parameters. The top four, called common something, are all common to all trace points, and then we've got arguments that are specific to trace points. So I can filter by adapter number, I can filter by the I2C address I'm reading from. In principle, I could even filter by the data if I knew that the data was a particular form. But this is how we can, in previous one I just assumed it was reg because the print format made it look like it was reg. In this case, the trace pipe doesn't make obvious what all the parameters are called, but I can go and look them up in the format and I can start filtering as I see fit. Beg your pardon, there we go. But what I'm particularly interested in is I saw that adapter 11 doing loads and loads of stuff, and I'm curious as to why it's so busy. So let's have a look at things a bit more deeply. So I'm going to try putting a stack trace, which is a type of trigger that you can attach to trace points. You can spell stack anyway. If you put the stack trace trigger onto the events, so I'm going to I2C read, which is the start of an I2C transaction. I'm going to set it up as the trigger. And now when I look at my trace pipe, I will be getting the stack trace of where this thing originated from, which is really great if I want to find out why it's hammering away. I mean, in this case, it's clearly hammering away because I'm getting continual interrupts from the board. So there's nothing in the software that we're doing wrong. It is just hammering away because it's constantly getting bombarded by something from the keyboard. If I want to go even deeper, I can change the trigger system. So I can remove the stack trace trigger with a shriek in front, and I can try looking at something called a histogram, which is where we start gathering statistics about the trace event. And you can control the keys that are happening. So I can say I want my keys to be the stack trace. So if I get, it will organise things by stack trace, and I'd also like you to organise it by adapter number, so that if we get different stack traces or activity on different adapters, it will gather it all up into the histogram. And what have I done wrong there? Pardon?
There's an extra R, stack trace.
Ah, I'll do it, yeah, thank you. Well, I'm from Devon, so we like the R's down in Devon. So that doesn't go into the trace buffer. The triggers are actually going to cause the histogram to accumulate these triggers inside the I2C read directory where the histogram can be observed. And if everybody knows what watch does, you probably won't have watch if you're on a busybox system, but watch allows me to observe the output of the system. I've been very careful while I was talking to you not to touch the touch parts of my laptop, so at the moment we're just seeing the data coming off the keyboard for whatever reason that is. When I touch my trackpad, as soon as watch updates the screen, we can see the second stack trace. If I was really patient, or you were really inattentive, I could also wait for it to poll my battery, but that, I think it only does that every couple of minutes. So you would also see, and that's the point where you see a different stack trace, because the stack trace going to the battery is it's about 3 times longer than these guys. And it's just a great way to start seeing inside the system. The histogram in particular is a fantastic way to start understanding why trace points have happened at particular moments. So the third secret of fantastic trace points is that, you aren't stuck with just the trace points that you started out with. You also have access to dynamic trace points that can be attached almost anywhere in the kernel. I say almost because the infrastructure needed to handle a trace point would re-trigger the trace point. So if you try and put traces on the trace system itself, there is actually mechanisms to prevent that because it would just dive into its own circular recursive loop. But other than that, we have the capacity to attach these probes to more or less anywhere in the system. And we'll start off by relying on the kernel's own resources. So I'm only using KAuSIMs at present to figure out what I'm doing. And I'm still sticking to my shell tools. So I'm going to create a trace point called VFS read. And I'm going to attach it to a function called VFS read. I've removed the underscores at the beginning because I didn't like that very much. And that will simply put a trace point upon a create the trace point and apply it. And it's created in a disabled state. What direction am I? So I have to go into events, kprobes, and I can enable all the kprobes, all one of them in one shot, which I've now done. And when I look at the trace pipe, I'll start to see VFS read activity starting to come out. As you would probably predict, it is the cat that is doing most of the read, so I'm still simulating this with my own read of trace pipe. There are ways you can filter out the activity that you're not interested in, that you're self-stimulating. But I've done this deliberately. Again, I've picked VFS read because you can intuit what's happening when I type and what's happening inside. Now this is not that exciting because I was also able to observe my VFS reads with ftrace already. But I can also stick ret probes on, which I shall do. So I'm going to observe the ret val, and there's this special dollars thing to do pre-canned particular activities. You can actually put stack traces in this as well with the dollars. And I'm going to append it to kprobe events. And what appending to kprobe events means, it means I'm going to add it without removing the old one. So you can either overwrite kprobe events, which removes all the dynamic traces in one shot, or you can append, which means my old trace point will continue to exist, and I can see the new one as well. So again, I have to enable it, and again, when I trace pipe now, I will now see twice as much activity, because I can now see every time we return and what argument was returned. At this point, I'm going to disable all my events again, because actually I'll do it wrong first. So I found that the VFS read was rather unsatisfying, because I can only see that it's being called. I can't see it's doing anything. So I'm going to try and do some machine level activity to find out a bit more about it. So I'll type this and tell you what it means, because it's in reverse form. So if you're aware of the ABI on ARM systems, then it's a RISC system that passes arguments through registers. So when you've attached to the VFS read function, then x0 contains the first argument, x1 contains the second argument, and so on and so forth. So I am using that knowledge to attach to the first argument, and I am offsetting it at 24 decimal, and from that pointer I'm then dereferencing that at 56 decimal. These are numbers I pre-looked up. You can look them up in GDB. There was a whole bunch of tools you can look them up with. But they are numbers that I have just pulled out of my hat in front of you now, and we'll come back to that in a minute. We can also do simpler things like look at x2, which is a count. So that's much easier to drag out. Sorry, x2. Much easier to drag out because I can. And I'm going to overwrite the kprobe events now, so this is the only kprobe in the system. And it's going to fail. And the reason it's failed is because I've left them enabled. And when I said you get yourself tangled in knots doing live demos with ftrace, this is main reason, because as soon as you try and manipulate the trace points, they never work. So I can go back in and I can just do a trace reset if I want, or I could enable them specifically. But because I've created trace reset to get me out of trouble, that's what it's for. So I can now put that in place, and when I cat the trace pipe now, it should get a bit more exciting, because nothing, because I didn't enable it, sorry, yes. So I go back and do the enable, cat trace pipe, and we can now see that we're reading a file called trace pipe. I mean, I know you already knew that, but we can now observe that every time we do a VFS read, we can see how big a buffer we were trying to fill, what the name of the thing is within certain limits. This is picking up a special short string inside the VFS system, and if you've got a really long file name, it won't actually give you the right one. But that's what we can do, and we can do that for almost anywhere in the kernel, and we can fish out these arguments, we can give them names. Once we've given them names, just as with the adapter number, we can filter on them. So not only can we can combine these bricks together, we can go and find an interesting function, we can extract interesting arguments, we can filter those interesting arguments, we can trigger on them to turn the trace on and off when particular interesting things are happening. However, it was rather kind of sucky having to know that this particular thing is at 56 hex. It's particularly sucky if you've got structure layout randomization turned on, because you have to look it up every time you rebuild the kernel. So we're going to stop using command line tools at this point. We're going to step up, no, we're going to use command line tools. We're going to stop using the basic toolbox of less and grep and cat and all the others. We're going to go and use kind of purpose-built tools that are more able to look at this stuff. So actually you can look at a subcommand of perf. So perf has a whole bunch of things. It kind of cut its teeth as a profiling tool, but it has many other things and debug features bolted onto it now. And one of these is probe, which takes advantage of the fact that perf is linked against libraries that can study dwarf information. So I'm going to look, I'd like to look at VFS read, just as I did before. And I'd like to put in a source level description of what I want to look. So I'd like a thing called iname. It's going to go to the argument called file. I'll dereference it just as I would in C. You can see I've got the dot there, which is not going to cause an offset or a redirect, and a final finger operator taking us to the iname. Need to format as a string, and I'd like count to come in, and I've just created count and count because I happen to know the local variable is called count. And I forgot to set the path. There we go, it's an history. So that is now going to create the probe using the symbolic information, and when we read it back, we can actually see that it's the same probe. You'll notice that it's picked text rather than the name of the function, because it didn't use k-allsims to find it, it used the debug information. And what that also means is if you're using a minimized k-allsims, you can still use the debug information to chase down static functions and other bits that are spread into peculiar places. You can also get a clue now about how I discovered the numbers 56 and 24. I'm far too lazy to have sat there and calculate them by hand. I did do this in the opposite order to which I've presented it. And once again, I can enable the trace point. It will do exactly the same thing, except that this directory will no longer work because the default directory when you use kprobes raw is different to the directory that perfprobe selects. So perfprobes, there is actually a prefix, you can choose what directories they appear in, but the default directory that probe uses is actually different to the one that kprobe events uses. But once I've done that, my trace pipe should look exactly the same as it ever did. Now, cross-tooling. Arm on ARM is coming, but cross-tooling is still a fact of life, and perfprobe is actually, by default, a cross-tool. It's not got any specific architecture burnt into it. So if I was on a PC, I could type perfprobe and I could use the -d, I'll get it from the history. I could use the -d argument, and it would pickle the, it will print to me the message I need to put myself into kprobe events. So I have it there. I can even, this has been picked up by using some clever distro knowledge of where dpackages install my current kernel. So I can provide it VM Linux and a path. I shan't type it out because it's rather dull, but I can provide that. So if I'm doing a cross development, I have to point it at my cross kernel. I can do this on my big powerful machine, and if I'm on particularly if I'm on a system like Android where I haven't got lots of other tools, I can just type this in, copying it from thing to thing. So it does work nicely with cross development. And then just to wrap things up, I'm going to go for even more calorific tooling, but it's still a very small one. I'm going to go for a BPF program called Ply. So Ply is implementing an awk-like mini language that allows you to attach BPF programs to trace points. So I'm going to start off with a little one-liner. It's odd because this is a one-liner I really quite like. So it's saying Ply, run for 5 seconds, that's the T5, and run this particular program, which will attach to a particular probe, in this case kmem cache alloc node. So it's going to attach to that function. And then the magic on the side is that @ is an anonymous dictionary, which I would like to index by stack. And every time this gets called, I would like to accumulate 1 in a counter. That's what all that translates to. So I have an anonymous dictionary that is indexed by the stack trace of the node, and I'm counting every time I run. And I can run that, and 5 seconds later, it will tell me which call sites are most active in calling kmem cache alloc. If you're really paying attention, you'll notice that this is semantically pretty much the same information as we got out from histograms earlier in the demonstration. So I think technically histograms are more efficient because you don't have to keep triggering the VM, but I actually prefer this one because it just fits my brain better, what's actually happening, and I see what's happening more clearly. And again, if I want to do filtering, I can do it in expressions inside Ply. So I've got access to the arguments of, the parameters of the trace point and everything else. So if I want to do complex expressions, modifications, and deciding things, I've got that option. But to fully round out the demonstration, I do want to show you something that you can't do with the tracing infrastructure on its own. I am going to copy and paste this because it is quite long. Oh, and I've got the directory wrong. Let me change it over here. So I'm going to drop this into the... I think I've already got it there from before, actually. Not my day. Right. I shall copy it one more time, and then I shall explain what it does. I was doing so well up to that point. That's what it is. So beg your pardon, there we go. That will now work. So what this is, it's 3 separate probes attached to 3 separate places. The first probe is attached to the entry of kmem cache alloc node, and it's a hack. And the reason it's a hack is because you can only get the stack trace on the entry. You can't get a stack trace from a rep probe. So from that beginning point there, we are grabbing the stack and storing it in our anonymous dictionary again, using the constant 0 to store it. And then when we return from that same function, we fish it out of the 0 point and use our return value, which is the address we've just allocated. That's where we put that. So in other words, what we're doing is we're taking the address that we've allocated in a dictionary form, and we are storing the stack trace in that address. And then on the other side, when we free the kprobe, when we free it from the cache, we remove it from the dictionary. Or in other words, we've now created a dynamic leak detector using eBPF, and that applies to any type of resource. So I've used KMM cache alloc because I know that my laptop calls it constantly, especially when it's on the network and talking to my other laptop to run the projector. So I can now just run ply, track ply. It will run those things until I press Control-C when it reports leaks. It doesn't just report leaks, of course, it also reports things that are still in flight. So you have to take a little bit of care, and in this case there is so much network activity happening that there is actually quite a lot of allocation. If you run it without the network, when I developed this demonstration, you didn't see leaks very often. You could occasionally if you rushed it, but there is a slightly sucky thing, which is these addresses have come in decimal form rather than hex, which is a shame. Ply is a very simple tool. You genuinely could go in and change the way it prints those if you wish. I tend to do a post-process to convert as needed. But that's about it, wrapping up. My script that I've been cribbing notes from as I've been speaking, I will make that the PDF available for this presentation, so you can dig out all these concepts again later if you're interested. And I think we had the 3 take-homes, did we? So you have to remember there's a README file. You have to remember that you can search for the static trace points with a find. And I view the static trace points as advice from maintainers. You know, that's the expert person working on the subsystem telling me what is most interesting about that subsystem. You know, I didn't have Mark Brown come and explain to me that Reg Map could show me how to read a register. I just went in and saw, oh, there's a Reg Map directory, excellent. And that finally, with the dynamic trace points, you can reach almost anywhere and do almost anything if you can figure out how to express it in hex, or you can use the perf probe to express it in C properly. And that's it. Thank you very, very much indeed.
Well, I'm not familiar with the underlying tracing system, so great demo, thank you. But what distinguishes static from dynamic trace points? You used VFS read as a dynamic trace point. Was it listed in the static traces?
No, it wasn't, no. So static trace points are effectively, they look like functions in the C source code. So in the kernel source code, there are macros that say, I have a trace point that I want to declare. You textualize it using this string. It has this arguments, and then that, in addition to storing the metadata, will also generate like a function stub, so that when you call that function, it puts it into the trace buffer. So it's very efficient, it's direct. I can't remember how it gates itself, but I thought it uses one of the static code mod type ways to gate itself on and off. Dynamic trace points are breakpoints. So underneath the hood, there's Masami in the audience, he wrote them. So under the hood, dynamic trace point puts a breakpoint. When the breakpoint comes in, it goes and looks up what address you've just hit, finds it in a table, uses that table to use the same data structure. So underlying it, once it hits the trace system, it looks the same, but the mechanism that you've called into the trace system is different. And then obviously you have to single step the machine, go through, put the trace point back, continue on your merry way. So dynamic trace points are not as efficient, but you've got to be... People are able to do quite sophisticated performance-sensitive network work despite the fact that we're breakpointing and stepping the machine.
So can you DOS your own box with dynamic trace points?
Can you denial service your own boss? So there are mechanisms to try and prevent it. So many of the functions that are intrinsically used by trace are marked no trace, and the kernel will prevent you from attempting to trace those functions. And the intention of that is to stop it doing a denial of service so that you can't have a trace point that triggers another trace point.
So if you stick it on a frequently called help function or something?
Yeah, if you stuck it somewhere at interrupt, which was called sufficiently frequently, I don't think there's anything that could prevent that ridiculously fast interrupt from doing it. But then that ridiculously fast interrupt was a bug in the first place, and congratulations, you found an over-frequent interrupt. You know, it's it was probably hurting you before, it's just now hurting you more.
Trace points are really, really, really efficient. So you would have to really try to find something where it would DOS the box. It would slow down, but you really have to try. You're more likely to cause trouble if you cat the trace file to your console and Control-C doesn't work.
Yes, and
Which I feel I've experienced.
I mean, the other really great way to deny of service the box is to set TP print K, which means that instead of using the efficient paths, it does a print K for each trace point. That will denial of service you almost immediately. And yeah, I've put some thanks up. So Stephen Rosett, who did a lot of the ftrace work, Masami, who's wandering around the conference and wrote the early versions of Kprobes, I believe, and Leo, who has contributed a lot of my knowledge about how debuggers and the debug technologies work. I will undoubtedly have missed people, but they're the ones who really technology were showing off, I think.
The only tool you referenced there that I didn't already have on my laptop was Ply, so I just googled it. But
I've put the URL to Ply, which includes build instructions and other things, is going to be in the PDF format. So yeah, and the warning about perf is that perf dynamically adapts to what libraries you do and don't have in the system. So if you don't have the dwarf dev files when you build perf, all those nice perf pro features get automatically disabled. So you do have to make sure you've got lots of development libraries when you build perf. Excellent, thank you all very, very much.